Hello and welcome to Unit 5, Waves and Sound, final unit in the 3U course. Today, introductory lesson is on waves and their properties. So what's today's goal? I want you to be able to explain the difference between a transverse and a longitudinal wave and give me their properties. Okay, so we're going to talk about what those two different types of waves are. So before we get there, we have to do a couple of get some background terminology done and taken care of so that both everyone has the same kind of background in terms of vocab. So what are waves? Waves are just disturbances that transfer energy over a distance. Okay, the sources of these disturbances occur from vibration. So earthquakes cause the ground to vibrate. When the plates shift, tectonic plates shift, so basically you have one plate trying to get over the other one. When you get that little shift, it doesn't have to be very big, you get a huge vibration. As soon as you have a vibration is an energy source. So vibration is an energy source. And we talked about it in the in Unit 3 about energy. There is always a transfer of energy. So if we have a vibration, which is a source of energy, that energy has to be transferred. And the way it's transferred in terms of earthquakes, if it happens underwater, we get tsunamis or tidal waves or surges because that energy is given to the water. Okay, if the vibration occurs over land, you get that huge shake that traditionally you see with earthquakes. I'm going to show you, or you'll get to play with tuning forks, and you get to see how what's called the tines vibrate, and that's what produces sound. And then similarly, if you pluck a string on a guitar, or you strike a key on a piano, which strikes a string, those vibrations will cause an energy transfer, and the energy transfer we're obviously interested is sound. So that's what we're kind of focused on as we go through. So the vibration source supplies the energy that's transferred through a medium as a wave. Okay, so it's transferred through the medium as a wave. Now, what is a medium? Right here, a medium is the same as saying what's the composition of some material or what's the wave passing through. So we talked about earthquakes. If they happen underwater, water's the medium. If you hit the tuning fork, it passes through air. If you're banging on one side of a wall, you are giving energy to the steel, which will then pass the energy through to the other side. So, two major types of vibration. And our two types of vibration are longitudinal vibration. So that's the first one. And whoops. No. There we go. A longitudinal vibration, okay, occurs when an object oscillates. Now, oscillates is a fancy word for moves back and forth, parallel to its rest position. And I'm going to give us a diagram in the next slide to help us out with that. But parallel is the important word there. The second type of vibration is a transverse vibration, and that occurs when an object oscillates or moves back and forth perpendicular to its natural rest position. So there are the two types, and the differences are simply that. One will vibrate parallel, one will vibrate perpendicular. Okay, so we'll come back to that in just a second. So what are some of the general properties of vibrations? You may have seen some of this if you've taken the grade 11 math, depends on where you are or how far you've gotten. So the terminology is pretty much uniform between math and physics. So a cycle is one complete oscillation. Okay, so one complete oscillation, they return to their original start position. All right, so that's what we call a cycle. Next term is the frequency. The frequency is the number of cycles per second. So how many times you do something in 1 second. So what's our formula? Frequency equals number of cycles. Number of cycles divided by time. And our units, if we have cycles per second, We call that hertz. All right, it tells you how fast something is vibrating. Okay, so it's hertz. Next, period. Period is the time required for one cycle to occur. All right, so period, often capital P, and that is time divided by number of cycles. So if you look at, there is a connection between this and frequency. It's also 1 divided by your frequency. Okay, so your units would be seconds per cycle, and basically cycles it's unitless, so it turns out just being seconds. Okay, just a time. So basically, and it's right there in the definition, period is the time required to do one complete cycle. So again, down below here, I just have stating that relationship. So frequency is 1 over the period, or period is 1 over frequency. So if you have frequency or you have period, you actually have more information, or you have the counterpart already. Okay? All right. Now let's get into this transverse versus longitudinal. So what I have is I have an example here, and what you want to do is you can draw 5 diagrams. That should be sufficient here. So I'm going to pause it, and you'll be able to see. I'll draw them up quick. And I just realized that you wouldn't have known that I went away or paused it, because I'm right back. Okay, so what I have here is the girl on the swing is a transverse wave. It's an example of a transverse vibration. Transverse vibrations, they oscillate perpendicular to the rest position. So what's the rest position? The rest position, if you're sitting on a swing and you haven't been pushed, your rest position would be just sitting there on the swing vertically. Okay, so I'll just put that in one diagram. So there's your rest position. Okay, so what happens when you're on a swing? Stage 1, you get on the swing. Stage 2, you're pulled back. Okay, so your motion would be backwards. In stage 3, your motion is actually forward. So the question is, have you completed one cycle in the swing? And the answer is no. Even though you're back to your original start position as a number 1, you are not heading in the same direction because we started off going backwards. So when we return to the rest position going backwards, then we've completed one cycle. In stage 4, we're then swinging forward, and in stage 5, we are swinging back. Okay, so one cycle, and I'll just put that down here. One cycle occurs when you return to your start position and have the same direction. So you got to be moving the same way you did originally. Alright, so there's one complete cycle. We're vibrating perpendicular, so I'm just going to put that in. See how we're vibrating perpendicular to our rest position. Okay. With the transverse vibration, we're basically it allows us to create graphically create a representation a lot simpler, a lot easier, and you'll see that in a minute, and I'll talk about that a little bit later on as well. So the next one, I'm going to draw up those 5 same sketches, look a little bit different, and you're not going to realize I'm gone. All right, so my example with a longitudinal vibration then is the hanging spring. So if you have something that's hanging from a spring, you have this urge as a student to pull on it and see what it'll do, which is good. It's nice to see that you have a curiosity. So number 1 is its natural rest state. That's how long the spring would be extended if we didn't touch it. So as we pull down, the spring will extend, and when it reaches that maximum extension, or how long you pull it out, it's going to want to return back to its natural state. It returns to its initial position, but now it's moving upward. So we haven't completed one cycle. We then go to maximum compression, and now it will want to start moving the other direction. We get back to that natural state, and it has now completed one cycle because we have a picture that's identical to number one. Now, longitudinal mass vibrates parallel to its natural rest position. So with the spring example, it's not leaving its natural rest position line, okay? Whereas the girl, she moved perpendicular to that natural rest state, okay? Here, we're moving on the line that we would normally be rested on. So that's the difference between a transverse and a longitudinal vibration, okay? The two of them, one's perpendicular and one stays parallel to the line itself. So let's analyze the girl in a swing with a transverse vibration. So I've got double axes drawn in here. The first one, we're going to go with horizontal displacement on the x-axis. So how far was she from the rest position? And for argument's sake, we'll measure that in meters. And then on the second axis down here, we're going to go with time in seconds. And the top one, we're going to go with distance traveled. I'll talk about it in a second. The second one is going to make more sense, so let's start with that. So if we go with, keep it simple, each box represents a second. All right, how did the girl's motion move? Well, at 0 seconds, she was 0 meters from her rest position. Let's say she reached her maximum, just doing this arbitrarily, she reached her maximum swing distance, so you pulled her back, and that took 2 seconds to pull her back. What happens then is you let go, she returns to her natural rest position. At 4 seconds, then she would move forward, move as far as she can forward at 6, and then she swings back at 8 seconds. So what happens is we get what we call a sinusoidal curve. Oops. So that forms a sinusoidal graph, something you may or may not have seen yet in your math course. But a sinusoidal graph is just a periodic graph that repeats itself. And that's what the girl's swing, if in an ideal world where she didn't lose any distance, that would be what her motion would look like continually. Now, up top here, what I did with the second axis is that this is a measurement distance traveled. She really didn't travel anywhere, okay? But what this is what we call length of one cycle. All right, so it's a measurement or length of one cycle. All right, and that's what we call wavelength. So for people that are in here that maybe have seen this in math and you're thinking, oh, is that not just wavelength by definition? Absolutely. But you got to remember, wavelength is measured in terms of meters, not in time. So that's why I had to put that up above, or that second axis up above. All right. So length of one wavelength, the period would be 8 seconds. Okay. But your wavelength is a measurement of actual physical length. Okay. In this case, it's actually 0. All right, so we're going to leave it at that for the moment. I'll finish the lesson up in the next video, and we'll look at transverse waves then and see how they look differently graphically.